Dear colleagues, today, I present research situated within one of the most dynamic and transformative domains of contemporary science, neuromuscular interactions. This interdisciplinary field integrates neurophysiology, biomedical engineering, computer science, and technology ethics, with a clearly defined objective, to establish direct and functional communication between the human nervous system and technological systems. At the core of this concept lies a simple yet revolutionary idea, that the electrical signals naturally generated by our nervous system can be translated into commands capable of controlling computers, prosthetic devices, or robotic systems. Within this framework emerges the brain-computer interface, BCI, serving as a mediator between the biological and digital worlds. What once belonged to the realm of science fiction has now become an experimentally validated and clinically applicable technology. To understand the significance of this field, we must begin with the physiological foundations of movement. Every voluntary action originates in the motor cortex, where an electrical impulse is generated and transmitted along the axon of a motor neuron toward the neuromuscular junction. The release of acetylcholine, subsequent membrane depolarization, calcium influx, and the interaction of actin and myosin filaments ultimately result in muscle contraction. This precisely coordinated biological mechanism provides the essential basis for the technological interpretation of neuromuscular signals. In practical applications, two primary methodologies play a central role: electromyography, EMG, and electroencephalography, EEG. EMG enables the recording of electrical activity produced by muscle contractions and its translation into executable commands, such as cursor movement, prosthetic control, or interaction within virtual environments. EEG, in contrast, captures electrical brain activity and offers more direct access to motor intention. Over the past 2 decades, advances in machine learning algorithms have significantly improved the reliability of signal decoding, enabling increasingly stable real-time communication between neural systems and external devices. The most compelling impact of neuromuscular interactions is evident in clinical practice. Research has demonstrated that individuals with tetraplegia can control robotic arms through decoded neural signals, thereby regaining the ability to reach and interact with their environment. Even more significantly, long-term BCI-based rehabilitation protocols have shown potential to stimulate neuroplasticity and contribute to partial neurological recovery in patients with spinal cord injuries. In this context, technology transcends its compensatory function and becomes an active therapeutic instrument. Beyond medical applications, numerous technological innovations are emerging, from brain-controlled wheelchairs to immersive interaction in virtual reality and advanced robotic system control. The integration of artificial intelligence further enhances the precision and adaptability of these interfaces, opening pathways toward more intuitive and responsive human-machine interaction. Nevertheless, the development of this field is accompanied by substantial challenges. Technical limitations include signal noise and inter-individual variability, while ethical concerns involve the protection of neural data privacy, preservation of user autonomy, and prevention of potential misuse. Consequently, the establishment of clear regulatory frameworks and sustained interdisciplinary collaboration is essential. In conclusion, neuromuscular interactions represent a pivotal step in the evolution of the relationship between humans and technology. By linking fundamental biological processes with advanced engineering solutions, this field enables the restoration of function, communication, and autonomy. At the same time, its continued progress must be guided by responsible and ethically grounded principles. If this balance between innovation and responsibility is maintained, neuromuscular interactions have the potential to become one of the defining technologies of the future, expanding human capabilities while deepening our understanding of the biological foundations of human agency.